so we're going to model real-world data. And so much of the data that we encounter in the real world may form a pattern. It's not always going to be a perfect pattern, but it's going to form some kind of a pattern. And so here we're going to take a look at the families of functions one more time. And we've talked about these, three of these specifically, and we're adding a fourth one into it, of being able to determine whether a set of data matches one of those forms or not. Back in earlier in the Algebra 2 book, we looked at the using constant differences and ratios. And we actually talked about this a little bit in Chapter 7. We were talking about exponential functions. That if we look at a set of data and there are constant first differences between the y values with evenly spaced x values, we knew it was a linear function. If we had to do a second difference between them, then we knew it was a quadratic. If it ended up being ratios, which is what happened with exponential functions, so if the difference between one number to the next was a constant ratio, we multiplied by 3, multiplied by 3/5. Okay? We knew it was exponential. And if we had constant second differences with this was the new one, square root. If we have constant second differences with the x values with evenly spaced y values, then we have a square root function. All right, so how many of you remember doing the differences like that? Okay, so if you remember it, then it shouldn't make it pretty easy then. All right. So when we're looking at a set of data, now a lot of times when you look at a set of data, you're probably going to be able to figure it out right away. Okay, this is linear, this is exponential, this is quadratic, this is square root. Okay, so first of all, it gives us, we look at the x values. So here we've got the time and year is our x values. And these are all evenly spaced. Okay? So that means that this could either be linear, quadratic, or exponential. Can't be square root because with square root, the y values would be evenly spaced, okay, possibly. Right? So we have evenly spaced x values. And so now we're going to find the differences between them, first of all. So we want to find the difference between 58, 93, 93, 128, 128, 163, and 163 and 198. Now, my suggestion is that when you do this, that you always work your way backwards. So start at the far right and go to the left. And then we're going to subtract them. So 198 minus 163 is 35. 163 minus 128 is 35, right? 128 minus 93 is 35. Okay, so all of these are 35. So this is the first difference. They're all the same, so that means we have this first one here, which is a linear function. So this would be a linear model. Or linear function. So this is a linear function. Because the first differences are all constant with the y values. Now, like I said, lots of times you should be able to look at them and kind of see. All right? So if we look at these values here, we have the time of year, 4, 8, 12, 16, and 20. And I'll give you a second to write these down. and these population values. And lots of times there should be keywords that give things away. And to me, this word right here, population, is a keyword. Because populations usually change by a percentage, which means then it would be which one? Would that be linear, quadratic, exponential, or square root then? Okay. If it changes by a percentage, that means that each time to get from one to the next, I have to multiply by a certain percentage then. And so when I see population, most of the time my first thought is going to be this is probably exponential. So I'm going to check to see if it has constant ratios. So I look at the time and year. My x values are independent. They change by a constant rate. Well, then I'm going to look at the y values and see if they have a constant ratio. So now I'm going to divide them. So we're going to do 8493 divided by 8847. And 8847 divided by 9216. And 9216 divided by 9600. Okay. I'm going to divide all these. Okay. And they should all come pretty close to what this very first one is, which is really nice because they use 10,000. And that's a fraction I can simplify. So now the one thing is that they may not be exactly perfect, but they're going to be very close. So a lot of times because of the ratios, they get us numbers that are really close to the right ones. But they're not always going to be exactly perfect, and we're not looking for perfect necessarily here, but something that's really close. So because these all give me the same constant ratio, then that means that my suspicions were confirmed that this is an exponential function. But most of the time, if they're using population, it's going to be exponential. Okay? And you just need to confirm it by checking. And you wouldn't necessarily have to check all of them, just check a couple of them and it would verify that. Let's look at letter C then. Here we have time in seconds, 1, 2, 3, 4, and 5, and the height in meters. So must be some object that is flying, maybe. Or being dropped, or let's see. At 1 second, it's 132 meters high. At 5 seconds, it's 0. So it probably something where maybe they're standing on a building, throws an object up, and then it goes up and then comes down. Okay. Well, looking at these numbers, what happens with these numbers? They're going up and then coming down, right? So when things go up and then come back down, that's the shape of a quadratic. And so I'm going to look at, I'm looking at my data. okay, what could possibly be happening here before I do anything else? And then see, okay, oh, it looks like it could be a quadratic, so it's probably going to be second differences are going to be the same. So here I'm going to do the differences. So I'm going to do it the first time with them. And remember, we're always working from right to left. So 0 minus 99 is negative 99. 99 minus 154 is negative 55. 154 minus 165, negative 11. 165 minus 32 is 33. Okay. So those aren't the same, but I didn't think they would be because I'm thinking it's quadratic, so that means I'm going to have to do the second difference, which means I've got to subtract those numbers again. So negative 99 minus 55 is negative 44. Negative 55 minus 11 is negative 44. And negative 11 minus 33 is negative 44. So since the second differences are the same, then this would be a quadratic function. So always take a look at your data first and kind of estimate what's going to happen there, first of all, and say, okay, I think it might be this, and then go from there. Okay. All right. Now, I want to look at these, check it out. I want to look at letter A only. Okay? Because if you look at letter A here now, you can see that which ones have the constant difference or constant rate? It's the y's, right? Instead of the x's. So in this case, if I look at these, all right, it says the square root has constant second differences between the x values even for evenly spaced y values. So in this case, the y values are evenly spaced. I would want to check the second differences with the x values then instead to see if it was a square root, okay? Which this one does end up being a square root. And if we look at 21, let's see. Or 21, look at letter B then, okay? That one's going to be a little bit different. So lots of times real world data isn't so convenient. In other words, it doesn't always turn out to be perfect the way we would like. And so we have to make sure at times that we are able to see what's the best fitting line. Because sometimes it might be two of them might actually give us a good fit. So first thing we want to do is we want to make sure that our calculator is correct with what it displays for us. So go to your mode on your calculator, and then you're going to have to go to the second page of second page of the mode. And make sure that where it says Stat Diagnostics, okay, that is turned on. We want our Stat Diagnostics to be turned on. Okay. Because if you remember, one of the things that we did in Algebra 1 and a little earlier in Algebra 2 is we looked at correlation coefficients. Do you remember using that terminology? Your diagnostics have to be on so that the correlation coefficient shows up on your calculator because it helps us determine what's the best fitting line for a set of data. So we're going to go back through the process of how to use our calculator to do is, and we're going to, now, since first thing they want us to do is we have a company that prints advertising flyers and tracks its profits. They want us to write a function that models the given data. So the first thing we're going to do with this data is we're going to put it into our calculator and make a scatter plot. And so from that scatter plot, we can make an estimate of what we think it might look like. Now, more than likely, your calculator is probably set up correctly, but we're going to check it. So go to second y equals, and we're going to look at plot 1. So you can hit enter on plot 1. Now, we want to turn it on, okay? So we can hit enter at the on spot. And we want the very first one, like our calculator is showing us here, that's a scatter plot. Because we have the different things are scatter plot over time, like we've done on our graph and our grades. Histogram, 2 different types of box plots, and I don't remember what the last one is. But we're going to make sure your X list says list 1, your Y list says list 2, and then we're going to use little squares. Okay. Now, all right, so it's turned on. So since it's turned on, if you go to your Y equals, you'll see that plot 1 is highlighted. So if you ever try to graph and, oops, I have some data in mind already, but if I try to graph it and you get where it says, it may say a dimension error or something. If you have any kind of an error when you try to graph, so it might be that you have a plot turned on, and the easiest way to turn that back off now is just go up to it in your Y equals and then hit enter, and it's now turned off. Okay, so we want it on right at the moment, but that's the easiest way to turn it on and off is just to go to your Y equals and hit on and off. Okay, all right. So we're going to take this set of data and we're going to put it into our list. So anybody remember how to get to the list? Well, there is the word list is up here above the stat key, but that's where we want to go is we're working with statistics. So we want to use the stat key. And so we want to go stat, and then we want number 1, which is edit. And then you should see these lists. Okay? Now, does anybody not have lists 1 and 2 showing up? Because sometimes when calculators are messed with, they lose the list temporarily. Okay, everybody's got lists 1 and 2? Okay. So to clear your list, if you have numbers in them right now, you can go to the list number and then hit clear and enter, and it'll get all that data out of there. And whenever you start a new one, a new set of data, you should always clear it, because if your new data has fewer numbers than the last one that was in there, and you forget to delete them, it'll mess up your information. So we're going to put 100 through 600, the number of flyers printed are going to go in list 1. And then our profits are going to go in list 2. So now we need a window to show this data. Now there is a quick way to make a window, but I want us to be able to think about it a little bit. So what should our window be for our x values? So when we go to, if you were gonna make your own scatter plot, okay? So if you were going to go to your paper and make a scatter plot, what would you go from the x's? So what are my numbers going to be here along the x-axis? Where? Okay, so that we can see all the hundreds, right? Okay, so we would start at 0, right, because we don't need negative values, and we would end up where, how far would we go down there then? Okay, should we go a little bit farther than that, though? Okay, all right, so we would end up going down here from 0 to 700, and we go by 100s, right? Okay, how about our y values then? What are we going to do there? Where would we start the y values at? Well, our smallest y value is 10, right? So we probably want to start at 0. We don't need any negative ones. Okay, we might eventually. I mean, we could have negative profit. And our largest profit value is 720. So then we're probably going to want to go to a little higher than that, so to 800. So we'll go set our window then. So I'll make this bigger. Okay. So we'll go to our window. Go from 0 to 700 by 100s, and 0 to 800, and we could go by 100 zeros. Right. So all we're doing is using the first numbers to establish our x values, second number establish our y values, and then if we graph it now, we should have a nice little scatter plot here. Now, the question is what's better? Because this doesn't look linear, does it? So it's probably either quadratic or it could be exponential. Right? Well, we could do second differences and ratios to figure that out. Okay? But there is a little bit easier way. And so I've written the steps for what we've just done here. Put the data in our list by going to Stat and Edit. So this puts our data in our list. We turn the scatter plot on. We did that. Now, to make a viewing window, we actually went and did it by hand, which will work really well. Or if you could press Zoom 9, and Zoom 9 actually fits a window to it also. So if I were to went here and press Zoom 9, then it gives me a very similar window to the one we had, but it's the window, the numbers aren't necessarily going to be the same. But it still shows me my curve. And so the nice thing about Zoom 9 is that it's a quick way to give you a window that'll show all of your data. Now, we want to find the best fit line. So in this case, we are either thinking that it's either quadratic or exponential. So if you go back to your calculator then, and if you press Stat again, and then go over to Calc, you can see here there are a lot of different things, but we're looking for regression, the ones that end in REG. We have number 4 is linear regression. Number 5 is quadratic regression. 6, maybe you have a cubic function is better. Maybe it would be a quartic function, so that's to the 4th power. And then we have, why they have 2 of these, but they have linear regression again. Ooh, number 9, that's natural logarithm regression. And then 0, we have exponential regression. So the 2 of them right now we're going to use is we're not sure, okay, is this quadratic or is it exponential? Which one's better? So we're going to try it with both. So let's do exponential first since I'm right there. So if you press 0 then, or go down to exponential regression and hit enter, you get this screen then shows up. Okay, our X list is in list 1, that's good. Y list is in list 2, all right, we're good there. The frequency list, you don't need to worry about that. And go down to, we want to go down to store regression equation. Right? What this does is it tells us where we want it to go. And so we can tell it to put it in y1 so that after I find it, it'll actually graph it then too, and I can see how well it fits. So there's two different ways to get to y1. And the easiest way is to go to alpha and then F4 or the trace key, where we have all of our y1 through y0. Okay? And then just hit enter right there for y1, and it'll plug it in there. Okay? Then we go to calculate, and it'll give us the numbers for an exponential equation. So in this case, it would be 9.55 times 1.00799 raised to the power of x. That would be our exponential equation. Now, if you look at your y equals, in the big number we're looking for here is, and I'm going to make a copy of this. The numbers we're really looking for are the r and r squared numbers, because those are the ones that tell us what's the best fit. The closer that r and r squared are to 1, the better the fit is of the line. So if you look at your graph now, though, you can see, or if I look at my y equals, you can see it put that equation to y1. And if I graph it, then it'll show the graph. And we can see from this graph that it's pretty good. Okay? Not great, but pretty good. So we want to check quadratic to see if quadratic will work also. So we'll go back to stat and over to calc. And now we're going to calculate the quadratic regression, which would be number 5. And so your screen should look exactly like it did when you did exponential regression. And then we're going to go down here and let's put this one in y2. So alpha, trace, and we're going to put it in y2. And then we'll calculate again. Now, I haven't figured out why when it does quadratic it doesn't show r, it just shows r squared. But you can see from this information that because my value of r squared, the value of r squared here is almost 1, where the value of r squared here is only at about 0.9, that the quadratic regression equation is much better fit than the exponential. And if we look at our graph then also, we can see that here's what an exponential looked like, and here's our quadratic. Notice that the quadratic went through almost every square perfectly, which means it's a much better fit also. So we can get rid of our exponential one because we know that one wouldn't help us to find any other information. Only the quadratic one is going to help us really find some good information. So then they asked us to find the best fit line. So my best fit line here is going to be that y equals 0.002 x squared. Okay, the value of a is 0.002. The value of b is 0.007, so plus 0.007x. And then c was minus 11.2. So that would be my regression equation. And now I could use that equation to be able to find other values that they're asking me for. So for instance, in this problem, they told us only the flyers between exactly 100, 200, 300, 400, 500, 600. Well, what if they wanted to know what's the cost going to be for 150 flyers? Okay, so maybe their goal is to make $200 profit. Okay, and so how many flyers could I use to make $200 dollars in profit. So we could actually use this graph then and use our calculator to figure out, because now I have a table. In my table, I'm going to want to go by hundreds, probably. Well, I won't, but in our table, okay. If I wanted to find out between 300 and, or make, what did I say, $300, so, or $200, between 300 and 400 would give me the $400. So I could change my window to start at 300, and I could tell it to go by 25s then if I wanted to, or I could tell it to go by 10s if I wanted to make it a little bit easier. And I could figure out that, oh, so we're closer to 320. So approximately 320, probably about 322 or something like that would give me my $200 I'm looking for. But by having the actual function, we can get more exact in other parts then.